ahead and Google it. You're going to find probably millions of hits. Any sort of accent you want, any sort of language you want, then you'll find some people with a sense of humor, without a sense of humor, people who can explain it better than me, people who maybe not quite as good as me. In any case, there's lots of ways of getting at this. If you want to look at that, you can go ahead and do that too. Okay, so we're going to start off with what is regression, and it's sort of like predicting. It's kind of fun in a sense because it's sort of like predicting the future. We do it every day. You look at stuff that happened in the past and you're assuming something like that is going to happen in the future. It may not happen, but it probably will happen. And one of the things we're going to be talking about today is, just as an example, is if you needed to make sure you get a certain grade in the course, you might think about, okay, what do I have to do to get that grade, to get a certain grade on an exam? You'll think, okay, well, what are the factors involved with that? One of them might be meeting with the professor, one of them might be talking to your colleagues about it, and another might be, okay, what did I do in the past to get the various grades I've gotten? And one thing could be, well, how many hours did I study? And you probably have in the back of your head, how much you studied and how much and what your grade was. So you've gathered some data just informally. So this is what we do all the time. You look around, what's your experience, what's the pattern of experience, and you predict a future event based on that. The world is not very simple a lot of times. There's a lot of different factors for your grades in this course or anything else in life. But we all use a sense of what experience we've had to kind of predict the future. And regression, in a sense, gives you mathematical tools to do that in a more precise and exact way. And a lot of medical science is based on this. There's a lot of things based on this use of regression that prove its utility. That so if you're testing a drug or something like that, you'll want to have a clear idea of exactly how useful it is in curing a disease or something like that. It's not really predicting the future, but it's based on the idea, common sense idea, that given a past set of data, hopefully we might see something similar so that we can prepare for it. Now, this PowerPoint that you're going to have available is going to have this table of contents. You can click on this down here below to get back to this table of contents, so you can sort through this. There's a lot of slides, but as much as possible I'm trying to give you all the information you might need. And in addition, you're going to have, of course, the videos available too. One thing we're not going to do is I'm not going to ask you to do the math. And so, every day we interpret statistics without really necessarily doing the math, and we can, get meaning out of them. So GPA, for example, so if I said, you had a GPA of 1, are you happy or sad? Pretty sad. Okay. GPA of 4, happy or sad? Pretty happy. Okay, so we use numbers in our everyday life, and we okay, if I asked you how do you calculate GPA, what statistic that is, you'd have to think for a second and say, well, I guess it's average, and you can kind of figure that out. Same thing with regression. I'm not expecting you to calculate that off the top of my head. I probably couldn't calculate it myself. I'd have to refresh my memory. But I can interpret the statistic. I can interpret the number, just like you can interpret GPA. Why is a 1 of GPA? Why don't you feel as good about a 1 than a 4? Do you just like the number 4 better? I mean, why is a 4 better than a 1?
It's higher on the scale.
It's higher on the scale, but so why does it make you feel better?
That means if I get A's, and you want to get A's.
Okay, so you get A's, but why are A's meaningful? How are they any good? GPA's higher, and got straight A's, and what do you do with those straight A's?
You get a better job.
You get a better job. Okay, so the number, the abstract number, has real world meaning. There's a context. There's a whole institutional context where we're trying to communicate to, what in part you're buying with your tuition is certification that we're giving the rest of the world that you know something, or you have the grit to at least get through 4 years, and that when they're hiring you, they're looking at that number and they're saying, well, this is what I'm getting for that. So that's a context that interprets an abstract number. Same thing with regression. There's going to be a set of numbers you look at, and you have to interpret it. You have to say, what does this mean? What decision do I make? Do I care about this? How do I care about it? How do I feel about it? Okay, so at the end of this lecture, hopefully you're gonna know about at least 4 numbers and one tool to look at called a Scatterplot. And what you need to do is understand them well enough to interpret them. You don't have to know the math. You just have to know how to interpret them. So I'm not asking you to understand the math. What I'm asking you to do is more like what a business manager does, or what a baseball player does. Just the baseball player knows a basic stat and basically how the game is played and knows how to interpret them. So a scientist might look at baseball this way, and most baseball players do not, are not breaking it down in terms of the physics. So we're not doing it this way. We are approaching this as a business manager would approach it. They're going to be given a set of numbers, and they're going to have to make a decision based on it. And there's going to be consequences if they're wrong, but it's also a judgment. You're looking at numbers and you're making a judgment. You have to decide what does that number mean in terms of a practical circumstance. So you're going to end up writing a memo. The last assignment is going to be a memo, 1-page memo, single space, 1 page. Second page is simply an attachment, which is your scatter plot. But you're going to have to tell the reader, here are the statistics and this is what they mean. And this is what I think you should think or do depending on what these numbers are. Same thing as we were talking about before. You have the inverted pyramid. Tell the reader in the beginning, what are they going to get out of this document? Why are they reading this? Tell them something about regression, why it's a useful tool. Go into some of the statistics, tell them what it means, interpret it, and then give them the takeaway, right? Same thing. So what we're going to do today is find out what statistics are they, how should you interpret them, and so on and so forth. And that's going to be the final project we're doing in this course. One thing we want to do in a sense is to define regression in relation to something similar to it, but what it's not. A lot of you talked about something called correlation in your previous discussion of descriptive statistics. So you could imagine a chart or graph in which you're looking at, let's say, increases, or let's say a graph of GPA and average GPA and responses to passion for major. And some of you looked at that. So it's 1 to 7. You can imagine along the horizontal axis, and then the columns are actually average GPA. And if you saw a smaller column to larger column, so as you increase in passion, you increase in GPA, you would say there's a relationship, right? You would say, okay, there's a correlation. Some of you use that term. There is actually a statistical tool that will calculate a correlation. And that's a linear relationship, a covariance. In other words, two things acting together. So in this case, it would be as your passion for major increased, your average GPA would increase. So that's a linear relationship. So correlation, which is not regression, is a tool that discusses a relationship between two phenomena measured numerically, and so two variables, variables meaning anything that you measure that has, different possible measurements, so variance and measurement. In any case, correlation is a measure of a linear relationship between two things. So as one thing increases, the other increases. It could also be as one thing increases, the other thing decreases. That would be also could be a linear relationship, could be a negative relationship. And we're not going to go into the math, but there is a mathematical formula to figure this out, and it's going to give you a figure, and the figure is going to be a percentage. And what that figure means is that the percent of, how much covariance is there. What is the percentage of change in one? How is that related to the change in something else? So, in very simple terms, the higher the percentage, the more the two things are related. So 5%, pretty low. 95%, that means, when one thing goes up or goes down, the other thing is going to change dramatically and in a very similar way. The thing you want to know about this is that the math is not designed or does not assume causation. Things can be correlated, but that doesn't mean that one thing is causing the other. They could just be in sync. Like good dancers. Like if people are dancing very well, that means they're very well coordinated. It doesn't mean one is causing the other necessarily. It could be that one's a better dancer, but you don't know that. You're just observing that they're dancing well together, right? Now, one thing you'll want to, write down, this will save everyone a lot of pain and anguish. Correlation is reported in the Excel output as multiple R's. That is not a regression. That is not something you're reporting in your regression analysis. So write down multiple R is in the Excel output. That is the correlation coefficient. So that's the percentage of variance. So, when you're looking at the Excel output, you see multiple R, that's correlation, and you can note it and look at it, but you're going to ignore it. So here's an example of correlation. You can see that here's some data about hours studying and then exam grades. And you can see one is 100% correlation and the other is an 86% correlation. And by looking at this number, you'll notice that the relationship between 9 and 6 is exactly the same magnitude of relationship as between the grade of 29 and if you were to divide these things, that would be exactly in this case this is going to be 66%. So those would be the exact same magnitude. Over here, when you're looking at these numbers, the magnitude of difference is going to be a little bit different from the magnitude of hour study. So you'll notice that these figures are a little bit different from the figures of an exact correlation. To look at it maybe in a way that might be helpful because we're talking about a linear relationship, you'll notice that as you increase the hours of studying, you see an increase in the actual grades. And so, real world, you're never going to have 100% probably correlation. But you might see real world some relationship. And so, in this sense, what you're saying is that 86% of the variance is related. So the relationship between change in hours of studying and the grade, about 80%, so there's about 14% is there's something else going on, is unrelated. So there's variance that's unrelated. Go ahead.
How do you tell that 86% is related?
You would have to go into the math. There's, which we're not doing in this course, but, there's people who came up with mathematical formulas to figure this out. And what we're doing is we're just understanding how to interpret the numbers. So to interpret correlation, you would say the change in the values in the two variables are about 86% of the change is similar or the same. The magnitude of that change, or 100% or 10% or whatever. So that's what covariance means. As I, in this case, increase in my hours studying, I'm increasing in my grade. Maybe 100% correlation, or maybe a little bit less. Okay, and this is what it looks like in a scatter chart. So if you were to choose in Excel, you want to look at this. The best way to look at this would be something called a Scatterplot. In this case, that would be 100% correlation. You'll notice the linearity of it. So in this case, the perfect relationship has a diagonal. It's not flat. It's a very strong diagonal in relation to the two axes. So that's 100% correlation. And you'll notice that you have over here hours studying along what's called an x-axis. So one thing you should remember is that x-axis is typically thought of as the horizontal. Later on when we talk about regression, that's going to be also the causal variable. But in any case, get familiar with that term. X-axis is horizontal, y-axis is vertical. Correlation, we're not talking about causation. Later on we will talk about causation. And this is going to be, the x-axis is going to be the explanatory variable, and the y-axis is going to be the dependent, or the variable that's being explained. But this is a good way of getting an idea of the relationship between these two variables. Now, real-world correlation might look like this. You'll see a bunch of dots, and you'll look at it and, get a sense of whether these two things are related. So from that set of dots, does it seem that hours of studying helps you, or is there a relationship, shall we say, between hours of studying and exam grade? Yeah. So the two things you're seeing is that not always. It looks like if you go from, let's say, 6 to 7 hours of studying, you're not really increasing your grade all that much. But then over here, when you get near 10, it jumps quite a bit, and the outcomes vary. It's not exact, but you can see an overall general pattern or trend. Okay, and so by looking at the scatter chart, you can see that there does seem to be a relationship. You can, over here, just imagine a line. Over here, you can have Excel put the line in the chart that's optimal. And this is going to be the regression line, which we'll talk about later. But the line it fits is the line which is optimal in relation to all these items scattered. See all the scatter here? Okay, this line is the least amount of distance. You could imagine many different lines that you could guess which would be the best line, but the mathematical calculation will be used by Excel and draw that line. That is the most efficient line if you want the least amount of distance between all those scattered dots. Make sense? And you can just tell Excel, I want to see that line. I mean, there's just an option in there. Correlation, even though it looks like maybe increased grades sort of causes an increase in, or increase in studying causes an increase in grades. That's not always the case. And we see correlations all the time that people make mistakes with. There's a controversy now where many parents are concerned about getting shots for their infant kids against a lot of serious illnesses because they've heard that some kids around the same age get autism. Has anyone ever heard about this one? And so the parents are refusing to allow their kids to get these shots. And one of the things that's happening is school systems are refusing to let those kids go to their schools because if you don't have the shots, you might end up with a deadly illness. And the science will say that there is no relationship between getting these shots and getting autism, but people see in their everyday life, I see kids, about this age, I see the kids have to get this shot, and I see kids being diagnosed about this age with autism, and I am not going to let my kid, I'm not going to risk it. Okay, so we do this every day. We see these relationships, make decisions on it every day. Okay, on the other hand, they might not be, and the science will say those parents are wrong, actually. And it could be that that the people who are concerned for their children are concerned that every year some kids drown in the pool or the local swimming hole, and they're also observing that kids eat a lot of ice cream during the summer. Now remember, when you were a kid, you were told don't eat before you go swimming because you get cramps and then drown, which actually turns out to not be true. But in any case, suppose you thought, well, maybe that's what's happening. So you're concerned with that. That's a correlation, though. It's not causation. What you would do with scientific approach, you would use better tools like regression, and you would think it through and more systematically and test it out. But it could be that there's a third variable out there, like it's summer, it's hot, so kids are eating more ice cream and kids are swimming. Okay, so that's correlation, and there's a lot of other things you could look at with correlation. A lot of relationships that people think of as are causal, but they're not. So this kid here is thinking, okay, every time that seatbelt light goes on, I start, feeling the plane bounce around. Okay, so you can forgive him for that misunderstanding. You could actually have a lot of fun with correlations. I mean, here you could actually suggest that we could stop global warming by just stopping the research. In other words, it looks like there's a relationship between researching global warming and the increase, in the average global temperature. So, if we simply stop researching it, then maybe it'll, we won't have a problem anymore. So, go ahead.
Did you ever see the one where pirates prevent global warming?
Pirates?
Yeah.
No.
Caribbean pirates, because they said there was no global warming back when they were around.
Okay. So bring back the pirates, and we'll be like.
Yeah.
You can do this all day long, and I found some if you wanted to control Greek debt or salvage the Greek economy, you could just ban Facebook maybe, because you see Facebook usage increase along with Greek debt. Or maybe people naming their kid Ava is causing the housing crisis. Or you could probably find a lot more like these. But the idea is correlation as a mathematical tool is not designed to look at causation. Stepping back from math to ideas, when you're thinking about a problem, you're thinking about, does this thing really cause, does A cause X, or is it just correlated? Now regression can do a lot more besides say, okay, what's the variance, what is the covariance, or how much does the variance relate to each other. It can do a bunch of other things, and we're going to talk about that. One thing you want to think about is regression does a specific thing, and we're talking about linear regression. We're talking about looking at the association between two things, at least, that is linear. There are other types of associations, so that regression wouldn't be good for those things. You know, regression is a tool. You only use the tool when it makes sense. It doesn't always make sense to use regression, and so you have to understand under what circumstances are you going to use it or not. Regression is only when you think X causes Y or A causes B. If you don't think that, if you think there might be just a covariance, then don't use regression, because regression is not the best tool. And in addition, it should be a linear relationship. In other words, as one increases, the other increases uniformly, or as one increases, the other decreases. That would be linear too, a negative relationship. If it's not your case, then don't use regression. And what you'll find is that regression will report very weak numbers or numbers that don't show anything. Let's get back to, just write this down, all this stuff on this screen, because it'll make our lives, go ahead.
Good question. Just to clarify, with the linear relationship, is it just as one increases, the other increases, or can it be as one increases, one decreases?
Exactly.
Could be both?
Could be both. They're both linear. I'll show you in a minute. One could be a negative linear association, the other is a positive linear association. As long as it's a line, straight line, diagonal line, you're good. Okay?
That's for correlation, that's not regression.
For correlation and for regression, yeah.
Does it have to be like increasing or decreasing like on the same scale? Or like if they're just both increasing?
They could be different scales, yeah. I mean, the scales, they usually are different scales. So if you had, if you were looking at hours studying and the grade on the exam, that's two different scales. So hours studying can be, 0 to 15, let's say, and then the grade for the exam is 0 to 100. Or you could say the price, square foot of a house predicts the price. So square foot is obviously very different from the price of a house. In regression, you're saying one thing causes another, and you're going to plot it out on a scatter plot, and there's going to be a horizontal axis and a vertical axis. The thing that causes the other thing is called different things. It's called the independent variable sometimes. It might be called causal variable. It'll be mapped always on the horizontal axis of the scatter plot, and that axis is called the x-axis, or the thing that causes the other thing. The thing that you're trying to explain is called a dependent variable often. It's always mapped on the vertical y-axis. It'll just help everyone if you just write that down and remember that stuff, because it's a lot easier. If you find when in your Excel output that the variable you're trying to explain, in other words the one that's caused by the other variable, is mapped out on your horizontal x-axis, then you reversed it. You made a mistake and you reversed it, and that does make a difference. So that's, one sign that you made a mistake in inputting the data is you chose the wrong data for the independent and dependent variable. Now, I can explain why they call it independent and dependent variable, but it'll take a little bit, of time. I don't think we need that. But briefly, I'll give you an example. A variable that is not independent and dependent would be if you're trying to explain, for baseball fans, if you were trying to explain batting average in terms of numbers of home runs. You're basically trying to explain something that is constituted by the same thing, because the number of home runs is part of the calculation for batting average. So you can't say it's causal. So very briefly, there's an example, but I could go into it, explain it further if you'd like. Okay. First thing you want to look at is a scatter plot, and a scatter plot is kind of a picture. We've already seen a scatter plot. A lot of the stuff I said for correlation in terms of interpreting the scatter plot goes with regression as well. Regression, again, is linear, and it's a tool that's only good for measuring linear relationships. There are some relationships in which two variables are related systematically, but they're not linear. Regression wouldn't be too good. It wouldn't be a good model to help you out. Regression is really just a model, just an idea, a guess that two things are related in a certain way. Real world, they could be related in different ways. Here you have a positive linear relationship. As I increase the hours I'm studying, I see an increase in my grade. You can also have a negative relationship. As I increase the hours, let's say I work or party, I see a decrease in my grade. That would be also a linear relationship. So if you had a theory or a hypothesis that was linear like that, then linear regression is great. But if you expect real world actually there to be a different relationship, then don't use linear regression. So over here, why would you expect some relationship like this curve there? As you increase in X, you increase in Y, but then all of a sudden it drops off.
Efficiency.
Okay, efficiency. So as you increase in what, you get more efficient.
Employees.
Okay, as you increase in employees, you get to a point where you're very efficient, and then you're adding additional employees, which is additional overhead, and let's say this is profit, and the employees are helping. At this point, extra employees are putting a crimp in your profit. Is anyone here an athlete? Okay, how about training? If you're increasing training, wouldn't that be good? Why would it ever decrease? Okay, so at this point, you have optimal training, and then now you're starting to overtrain, and your performance is going to be, you're getting hurt, you're getting tired, you're burning out. You don't want to use linear regression because you don't expect always, as you go up, to keep going up. Regression can be weak or strong. Now, how do you know that? Again, regression is simply a mathematical line drawn in terms of and in relation to the actual data. These dots are each pieces of data that are defined as the value of the dot in terms of the X and Y axis. So this is, if I studied 1 hour, let's say that right there is a grade of 60 or something like that. Okay, so if I study 1 hour, and if I study 2 hours, it's a grade of 70, and 3 hours, a grade of 75. So you have that relationship. It's just estimating that relationship. How good that line is in predicting an answer to the exact grade you're going to get depends on what's the scatter around that line. So if I studied 1 hour or 2 hours here, I can see that line which predicts, right, that's the value it predicts, that's the grade it predicts, where that line crosses the two values you're looking at, but those two dots are the actual values. So real world, you can use either one of those. What regression is going to do is going to give you a prediction, which is an abstract line, and it's going to predict exactly there. Based on, of course, your past data, but the future prediction is going to be this place right here on the line, when indeed your actual data in the past was not on that line. Regression is more useful if the past data you were working with is actually much closer to that line. You know, if you care about the outcome, which is y, you'll want that line to be pretty close to an expected real-world outcome, right? That's a weak relationship. In other words, that's regression where you have the dots, the actual data, far away from the estimate, and that's a strong one. And this is just weak and strong in terms of a negative relationship. That's perfectly fine. If you expect a negative linear relationship, then use regression. So regression is just a mathematical estimate of a line, and it's only useful for two reasons. One, that the dots are close around that line so that you're going to see that the line can actually predict something that's useful. And the second thing, that is linear. What would no relationship look like? In terms of all those scatter plots we just...
Random points?
Just random points. Where would the line be? It would actually just be the average of the y variable, the dependent variable. So it would look like that. You really couldn't do anything more than report the average of, in this case, grades. What you're seeing is that no matter how much you study, doesn't make any difference. You could have no relationship in which dots are very close to the line, so it seems like, okay, that line's helping you, but it's really not, because it's, you know, increase in studying, which is the x-axis, is not really helping you understand the increase in grades. So that's actually a picture of, you know, no relationship between two things. Here's a perfect linear relationship. This is what it might look like. This is not what you're going to see in your output. Real world is always a lot messier than this, but to start off with, it's nice to see a perfect relationship. This might be a regression output, a real world hour studying, predicting grade. This might be what you see. How do you want to interpret this? Does there seem to be a relationship between hour studying and exam grade just by looking at this? Should you study more if you're interested in getting a better grade? Is it going to be the only thing you should do, or, you know, is it explaining everything? Does it seem to be explaining everything?
No.
Does it explain a lot?
Yeah.
Okay, so let's say we agree it explains something, but looking at, you have to sort of decide at a certain point, is this explaining a lot? Is it explaining everything? Is it a very strong component in explaining this or not? So how can you tell by looking at this chart? Let's do two things. First thing, why do you think there's any relationship at all? And the second thing is, how can we gauge the strength of this relationship?
By seeing how much the plots vary from the line.
Okay. So one thing you're doing is you're looking at the actual values. In this case, here's one grade you have. You got a grade of 48, and you studied 6 hours. And here you studied 7 hours, you got a grade of 49 or 46 or something like that. Let's say 47. You know, so that's what these values are, and this is the sort of predicted line, the best fit line that you're going to use to estimate your future grade based on. So it's not perfect around there, but it looks like those dots are near that line, so that's a good thing. Now, how do we know that? We just saw a line before in which there was no relationship between the two things. There was still a line. You could still draw a line there, and the dots could be close to the line. When there's no relationship, how do we know there's a relationship? Just by looking at that line or looking at the dots. Go ahead.
I guess like the higher the study per hour, and they you still get like a higher grade, but like around maybe around 16 hours and 20, you still get
Yeah, it keeps going up, so the dots are around the line, but the line is going to be at an angle there. It's going to be, it's in relation to the two axes. If there's a relationship, you'll see a strong angle between the two axes. The optimal, ideal one would be starting here, down at the bottom, and then working your way up to the top. That would be a perfect relationship between the two variables. You're probably never going to see that in the real world. It's always something like this. So this line is not as steep. The slope of the line is not perfectly steep, which shows a perfect prediction. It shows a partial prediction. It gives you some idea of every time you study an extra hour, no guarantee, but you have an additional chance of getting a better grade. Here's all the stuff I just said, is understand how to interpret a scatter plot. So you're looking at how the slope of the line, how is the line angled in relation to the axes? How are the dots grouped around that line? That's the kind of thing you want to look at. And that gives you an initial sense of whether the linear relationship exists or not, and how strong it is. Bless you.
I have a question. So, for interpreting Scatterplot, and one of the things you look at is the slope of the line, and say like the slope is like pretty high, like pretty angled pretty
Steep, yeah.
steeply. So we're to look at that. What would you like say about that in your interpretation? Like the steep slope of the line said that the relationship.
Very strong.
Very strong.
The only thing you can't say is whether in other words, the only other thing you would look at is whether there's a lot of scatter around that line. In other words, if you saw the angle very steep, you would say there's a strong relationship, but you would then have to look at the scatter and say, well, how accurate is that line predicting outcomes? Because if you saw a lot of scatter around the line, then real world, there's a lot of variance going on. We'll talk about that in a second. Okay, just a quick thing here, just so you know, regression requires that you have numbers. You got to have variables that have, what you want is data that has a certain logical hierarchy. At the very least, you want a hierarchical, 2 is better than 1, 3 is better than 2, etc. And they've got to be numeric. They can't be gender, male, female. If you want to get technical, you could use a dichotomous variable, but we're not going to go into that in this course. So when you're doing this, forget about categorical variables like, what color you like or something like that. What's your favorite color? Because that's not, you can't quantify that. So you're looking at numbers like age and salary and things like that have a definite numeric difference in values that you can measure. Okay, so now we're going to get into you're going to have 4 statistics, just like average. Like we all know, GPA, we can interpret GPA, right? That's a statistic we have meaning, we have feelings about, and we know how to interpret it. So what we're going to do is we're going to talk about at least 4 statistics you're going to get out of the regression output, and we're going to figure out how do we feel about them. When we look at them, how do we interpret them, and then how do we feel about them? And here's the overall sequence. You don't have to understand this right now, but understand that this is in the PowerPoint. It's going to tell you what the overall sequence is. But in general, the first thing you do is you look at the scatter plot, and then you look at something called significance F, and so on and so forth. Okay. So that's in the PowerPoint, and we'll go over it today and probably next time. And I'm just about to go over that again, but here it is in the overall sequence. First thing you want to look at is reliability. There is actually, when you're using regression, Excel is going to spit out a number that you want to look at, and that number is the estimate that the data, you could think of it this way, as the data is garbage. In other words, that the data is not reliable. So we talked about, this is very similar to when we talked about outliers, and how outliers make the mean and the standard deviation unreliable. So Excel, and in the math it does, is going to spit out a number. It's called, actually I should change that. It's called in Excel, that's going to be called significant F, and pH status could be called a p-value, and that's an estimate. It's, you could interpret that as a percentage, the chance that there's something wrong with these statistics. There could be an outlier, there could be a problem, so that you should not, you should at that point you should just ignore, you should stop, because every regression statistic you look at is unreliable and you don't want to depend on it. So you could think of that in the same way as, we talked about an outlier, and whether looking at the mean and standard deviation is useful. So what's an example? If I wanted to get a sense of you as a group, of this class as a group, I could ask, okay, what's your, I wanted to find out, how brilliant my students are in relation to other students, so I'm going to ask you what your GPA is. Okay. Now, what can be an outlier that might suggest that the average GPA I get out of this group this is actually misleading me? It could be, maybe there's a student in here that somehow is surviving in this program that has a GPA of 1. That's going to change the average GPA in this room quite a bit. And so that's an outlier. So the average GPA is really not helping me understand the GPA for this group. Or if I wanted to understand salary, what's the average salary of a typical student? And so if one of you turns out to be Donald Trump's nephew, what does that do to the average income and available disposable income in this course? That, now you have a disposable income of $3 million apiece. Isn't that nice? But does that tell me really about this group? No, that's garbage. That's misleading me. Same thing here. You don't have to understand the math, but here's the estimate that all this is nonsense. And the way to interpret that is simply to say it's going to come out as a percentage, and that's the percentage chance there's something wrong. The rule of thumb, the accepted percent chance that everything is nonsense, is 1 in 20 or 5%. If there's anything less than that, then you're fine. It's even better. Okay, so that's called the F. Excel will call it significant F. pH stat will call it p-value, but that's the first step. Second one is the coefficient of determination, and that's very much like correlation we were talking about, the percent of variance explained. Coefficient of determination is simply actually the correlation, squared. Or actually the square root of the correlation. They are mathematically related, which you don't have to know about, but you'll notice that if you multiply the correlation by the correlation, you'll end up with the coefficient of determination. Again, you don't have to know that, but in case, but how do you interpret that? That's going to be interpreted as a percentage. So Excel output will give you a number, and it's going to call it R square. Okay, and correlation is called multiple R, just so you remember that, but R square is the coefficient of determination. And the way to interpret that is the percentage of variance explained. So it's just simple percentage. That means how much of the dependent variable of the thing you're trying to explain is in fact explained by this one variable, the independent variable, the variable that's the explanatory variable. What percentage? And that means that answers the question, how important is this? So if I were to say to you, okay, the coefficient of determination of hours studying and the grade you get on an exam is 3%. Are you happy or sad? Are you confident about studying and using that as a way of getting the best grade or not? Suppose I said it was 95%. How do you feel about the strategy or idea of studying extra hours to get that grade? Happy or sad? What's that? You're sad. 95%? 95% of the variance is explained by studying. You're trying to find out, your question is studying going to help me get that grade? Because I want to improve, I need to get a good grade in order to pass this course with a certain grade so I can get my GPA to a certain level. That's my goal. I want to know if studying is important. Okay? If studying can explain 95% of the variance in grades, that's explaining almost everything. So in that case, you would say, I will take studying hours very seriously. If it turns out to be 50%, how do you feel? It's important, but there's something else going on too that's affecting your grades that you should be thinking about too, right? Maybe. If it's 2%, how do you feel? Then I probably wouldn't study extra at all. But there is a relationship, but it's only 2%, so it's weak. So that's how you interpret it. It's a percent. It's how important that is. Coefficient of determination. Second thing you want is you may want to predict exactly what grade you'll get depending on how many hours you want to study. Now, if we already know, let's say we're already convinced that studying has a relationship to the grade. Do you study 1 extra hour? Do you study 40 extra hours? Wouldn't you want to know? Wouldn't it be nice to have an estimate of exactly how many hours do I have to study to get exactly what grade? You don't care? You're just willing to study infinite number of hours and 40 hours? Go ahead.
But like, just because like the graph tells you kind of like, if you study this amount of hours, it can be different from like everyone else.
Yeah, but let's assume that you've even taken you've written down yourself. You have a journal and you wrote down how many hours that you've studied and what your grades are. So, I mean, you're right. I mean, if you're looking at everyone studying and their average and then their grades, it's for you, that's not that may not be quite as helpful as if, but in this case, let's assume you had your own data, so it's you. Okay, so now we can start to get pretty much. The next thing we're looking at is slope. And if you recall, remember that scatter plot, the angle of the line, and if the angle of the line was steep, we liked it, and if the angle of the line was flat, we thought, okay, there's no relationship, right? So that's the slope. The angle of the line, the steeper it is, this Excel is going to spit out a figure, and that figure is exactly how much increase in your grade are you going to get for every increase in your x, your independent variable, in other words, your every hour increase in studying. So for every hour increase in studying, what's going to be the increase in the y-axis, in the dependent variable, or in your grade? So it's going to tell you, if you want a grade of 85, you need a grade of 85, it's going to tell you you have to study, let's say 10 hours. The regression will give you an estimate, will give you an idea of exactly how much you want to study for that grade. Okay? Now, the way you calculate that, you would also need something called the intercept. And so this is the way of looking at it. Excel is going to spit out a number, which we're calling the slope, and that's the angle of the line. It's a mathematical calculation of the angle of the line. And then the other thing we need is the intercept. Where do you start? And that's going to be where the line crosses the y-axis when our studying the dependent variable is 0. Okay, so you start here with the intercept. So Excel is going to spit out a number. It's called the intercept. And that's where, your independent variable, in this case our studying, is 0. And then you add every unit of x plus the slope. The slope calculates the angle of the line. So it's going to be, in this case, you would take the intercept, which looks like about 43 here, right? And then as I go up 1, 2, 3, 4, 5, it looks like 5 units of x, or the independent variable. It looks like I'm getting up to a grade of about 54. So the slope is going to be each unit of x times 5 equals about 54. So again, you're starting with your intercept, and then you're simply calculating how many units of x am I interested in? 5. And then you take the number it spits out called the slope, you multiply that, and that's going to give you the estimate. And that gives you your estimated grade if you study 5 hours. Are you necessarily going to get that? We'll talk about that in the next step. Probably not. But the regression line will also give you a range to expect. Okay, makes sense? So in this case, we're talking about an intercept of 43. We're saying, as you increase in your each unit here in our studying, you simply multiply that by the slope. The last thing we want to look at is standard error. And you'll notice these dots are not exactly on that line. So the regression line is going to give you a prediction, a certain grade, let's say of, in this case, 54 if you study 5 hours. But as you can see, that's just an estimate. There's scatter around that line. So real world, what should you expect? The regression statistics will help you with that too. It'll give you a range to expect around that estimate. So if I said to you, you know, it takes about 20 minutes on average for me to drive home, does that guarantee that if you came to my place to visit, that it's going to take 20 minutes from here? You know, what might happen? It could be traffic. It could be maybe some of you are, you know, speed. Maybe some of you got a Maserati or something like that, and you know, maybe you got a police escort. I don't know. So you could get there a lot more quickly than I do. You could get there, you know, a lot later because there's, you know, a lot of traffic. And so what else would you want to know except that, you know, my general estimate of 20 minutes? You would say, you would also want me to tell you, yeah, there could be a lot of traffic, so, you know, I would make sure you leave maybe 30 minutes in advance just to make sure you get there, because there's often a lot of traffic. Okay, so the next thing that the regression is going to do for you is going to say what is your expected range around that estimate. And that's the standard error. Okay, and it's going to give you a figure. And the figure is expressed in terms of the dependent variable, in other words, what you're trying to explain. So in this case, if we're talking about grades, let's say these are points. I should have, you know, expressed them as points instead of percentages, but in any case, if these are points, if you had a standard error of 9, that tells you whenever you're looking at a particular estimate that real world, you should not be surprised if your grade ends up 9 points above or below that estimate. So if you really needed, let's say you really needed this grade, I need a grade of 65 in order to pass this class. So I need to, it looks like I need to study 10 hours. Is that a good idea given this standard error? You need a 65, which is about here.
So, no. Yeah, that's probably a little more than that. You probably want to go closer to maybe about 15 hours.
15 hours will put you up here, and then the standard error will be above and below, let's say 76. So that might.
13 hours, just in case you go under the.
So you might want to study that. You know, you might want to study 16 hours because then that range is going to be well above what you actually absolutely need.
If you went your lowest, like 9 points lower, you still pass.
Right. This is giving you. This is telling you. Don't be surprised if your grade is above or below that. That's pushing it. Okay, we'll continue with this next time. So if you run this analysis, we'll use the example of hours studying and exam grade. And, you know, this is something, you know, I would take notes on this, make sure you understand this is you know, you need to understand what this scatter plot is showing us and how it's laid out. This is the x-axis down here, the hours studying. And that is going to be what kind of variable? You know, you have your independent or dependent variable, and up here in the y-axis you have exam grade. Go ahead.
The x is the independent.
Right. And so what's causing what?
So whatever is down here, the x-axis is causing what's up on the y-axis.
Exactly. So whenever you see one of these charts, you have to make sure it's configured in this way. It's the x-axis down there at the bottom is always the thing causing the variable mapped on the y-axis. In this case, you're assuming that there are causal relationship. In other words, hours studying before a test can cause, your thinking might cause an exam grade to increase or decrease, right? Getting an exam grade after you've studied can't cause you to go back in time and study that much. So there's no way you can have a relationship between exam grade or exam grade causing. Okay, so that's the kind of relationship that regression you want to look at. In other words, you can't think of a way in which the reverse would be true. And what you're looking at here is the scatter. So here's the data, the actual score. So each one of these dots is going to be a piece of data, one person reporting that they, looks like they studied 3 hours, and they got a grade of, or I think this is one person and their experience, let's say. Let's say it's, you've recorded your number of hours studying and your exam grades. And you've studied for 3 hours, and you got a grade of 55 or something like that. So that's what that dot represents. So as you study more, you can see that your grades get higher and higher and higher. And it looks like a linear relationship. And Excel will actually fit a line in there and show you the best ideal line to think about that. The model, the metaphor, the image, you know, to conceive of that relationship. Okay. So correlation provides a percentage. That's the percentage of variance that is in sync. You know, so as the values of one variable get positive, the other gets positive, or you know, they could get negative in the opposite direction. You know, what's the proportion of change in one that's related to change in the other? Regression is going to give you a lot more tools. It's going to give you these 4 tools here. One is the variable important? In other words, you want to know the percent of variance explained. It's called the coefficient of determination. It's called the power, perhaps. So one thing you want to know is studying important? How does that report? How does regression report that? Just like correlation, it gives you a percentage. It gives you the percent of variance that the one variable explains in the other. So 0 to 1. And you have to interpret that. So for example, with the number of hours studying, if you had 86% of the variance explained, how do you feel about the importance of hours studying in determining what your grade eventually ends up being? Real world is there's always lots of stuff going on. There's lots of things, lots of variables out there. Some you can measure, some you can't. So it's very rare that you're going to measure something and find, you know, close to 100% variance explained, unless you're in the unless you're in the natural sciences. It's just the world isn't that precise. But you get a number and you have to interpret it. So how do you feel if hours studying explains 80% of the variance? Versus how do you feel if hours studying explains 15% of the variance? How do you feel? You want to know what exam grade you're going to get. You want to know how many hours do I have to study to meet my goal, to get the exam grade that I want. And this variable explains 15% of the variance in the grade scores. That means 85% of the variance is not explained by studying. How do you feel about that? Is this variable useful to you, or is it?
85% of it is not like explained by variables, no, because 85% of those is too much.
Right. So you're going to look elsewhere, right? You're going to say, well, if 85%, that doesn't explain much. You may still look at it. It still does explain 15%. Now, let's just do the reverse. Suppose it explains 85% of the variance in exam scores. In other words, which exam score you get is actually is related 85% of the time to the hour studying. Now, how do you feel about it? I would now think about studying more, because that's an important thing. Okay, so that's one thing that regression will give you. The other is precision. You may want to know, how many hours do I have to study exactly in order to get the grade that I want? Now, let's suppose you need to make sure you get a grade of at least 70 in this exam, or you're not going to pass the course, you're not going to graduate, and you're going to be here an extra semester. You also have a tight schedule, and perhaps studying isn't the most fun thing in the world. So wouldn't it be nice to find out exactly how much do I have to study to meet that goal? Otherwise, you might study for 40 hours just to make sure you get the best grade possible. If you can study for 12 hours and you're pretty sure you'll get the exact grade that you need, wouldn't that be nice? So what regression can do is actually predict what your grade will be based on your past data, your past experience with that. And that's called the slope. And that's a prediction, an estimate of what your grade will be given a certain number of hours studying. Kind of cool, right? But that's just an estimate. Regression is also going to tell you how scary that estimate's going to be, how varied your real life experience will be. So I can give you my opinion. For example, it's going to take you 30 minutes to drive to Denville, but I can't guarantee it's going to be 30 minutes, right? There might be traffic, there might be an accident. I don't know how you drive, who knows, you might stop for coffee. I don't know. There's lots of stuff happens. Well, regression will also include a term which says, here's the range, the likely range that you'll actually see. So let's say the regression suggests that if you study 10 hours, you will get a grade of 72. It will also tell you how many points above and below that you should not be surprised to see. There's a likelihood of a range above and below that. And let's say it's 9 points, and you need a 70. Do you like that? It's called standard error. And standard error is 9 points. And the way to look at that is you have to understand and expect that you will probably see a grade 9 points above or below the estimate, which is 72. And you definitely have to get a 70 or you don't pass this class. Do you like that result? In other words, 10 hours of studying will give you a 72, but it's going to give you that range around the 72. Do you go with that or not? If you get a lower grade, you are going to be back next semester. Okay. And then finally, besides that, we have reliability of the data. So if you recall, the test of reliability is similar, once again, to the test of outliers. In other words, if there's something strange with the data, then don't trust the regression statistics. So if there's something strange with the data, you don't trust the mean and standard deviation, right? So we talked about outliers and why outliers will actually just make those, statistical figures misleading. Same thing. Now, I am not expecting you to understand the math or the logic behind it, but there is a test for that, and you need to know how to read that test just to determine whether the data is garbage or not. And so that's the 4 pieces of information you're getting out of regression. So you're getting a lot more detail than you do correlation. So again, you're getting a coefficient of determination. That's expressed as a percentage, the percentage of variance explained. That tells you how important the variable is. Is it important or not? Are there other factors out there that you may need to look at? How much do you want to rely on this one variable? Again, you can get an exact, at least estimate, guess. You can get to Denville in 30 minutes, but there's no guarantee. Here's the Excel output. This is what you're going to get from Excel. I've highlighted all of the things you need to look at in yellow. And this is the coefficient of determination. This is how strong the relationship is. So you can see 0.73, etc. You can read that as a percentage. So 73% of the variance, notice it says R squared there. That's Excel speak for the coefficient of determination. And that tells you the variance explained. So is that a lot or a little, or how do we feel about 73% of the variance explained? Okay, we're unsure. Does it explain nothing, something, a lot? It explains some of it. It explains, 73%. Also, that also means that, 27% is not explained. Social science, that's a pretty strong rule of thumb is, something below 30 might be considered weak. Some will say up to 60, between 30 and 60 is moderate, and above that is extremely strong. Because in social science, you can imagine, is a very inexact science. Because if I'm giving out a survey, maybe some of you are tired, don't care about the survey. You always have a lot of noise and garbage in the data. So you're looking for some association. You don't expect an extremely strong association at all times. Okay, what does the standard error mean? This is 0.08. And that is actually expressed in terms of the dependent variable. This number here and that number here, which is the slope, are read as the dependent variable. Now in this case, the dependent variable is grades. So what is this 0.087 blah blah blah? What is that telling us? If we're starting with 0 to 1 in terms of grades, that's our scale. The standard error is the range around the estimate that we can expect to see. So we could expect to see an 8-point range above or below the estimate. Now where do we get the estimate? That's down here. It's called the slope. And then 0.02. So how would you read 0.02? Now you could think of our scale right now is 0 to 1, but you could think of the grades as points from 0 to 100 points, right? So how many points is 0.02? 2. You know, so if it makes it easier for you, just convert it to points. Doesn't matter. What this means is approximately 9 points. Just round it up. 9 points above or below the estimate. How do you get the estimate? This is how you get it down here. You're going to start with something called the intercept, and you're going to add the number of units of x, which is the number of hours you're studying, times the coefficient. That means every hour you study, you're going to get 2 extra points on your exam. Okay, so the intercept is this thing here. This is where the line goes across the y at the place where your x is 0. Okay, and I'll tell you in a second why you need to understand the intercept. You know, so if you don't study, what that means is you will get a 43 on the exam. The estimate is, this regression model is going to say that what the intercept means is that if you don't study, you will get a 43. Now, how do you calculate exactly how much hours studying? You use the intercept. You start with the intercept because that's 0 hours studying, and then you look at how many hours of studying you're doing, and then you multiply that by the slope. So as we said, the slope is 2 points. The intercept is starting at 43. I'm just rounding up. And then so you have to decide how many hours, you know, what's the grade I want, how many hours do I want to look at, and what grade would I get. So the formula is simply starting with the slope, 43, and then you add how many hours you're thinking about studying, 15, right? And then you multiply that by how many points that the model estimates you will increase for every hour studying. And again, that comes from down there. Intercepts comes from over here. And so you would get a grade of 73. Now that would actually meet your goals, a grade of 73, right? So you know you have to study probably 15 hours, maybe 14 hours. So it gives you an idea. There's some information you didn't have before. You know, before you had no clue how many hours you need to study. Now you have solid information based on your own history of how much studying you have to do. And you'll see what the slope means. As you go up this 5 points, you see the angle here of this line? As you're going up in number of hours studying, you see the angle is bringing you up and increasing the number of exam, or the total exam grade you're going to get. So you can imagine a triangle right here, and the steeper this line is, the stronger or the larger amount of exam grade you'll get for each unit of x. The more flat the line is, we talked about before, if that line is flat, the more you study, you're still going to get that grade. So let's say the grade here is at 43 and it's a flat line. That means as you study up to 25 hours, nothing happens. Your grade stays the same. Okay, standard error, like we talked before, is you can estimate here 73, that meets your goal, but regression will also tell you, real world, don't be surprised if you see a range around that goal. It's sort of like the standard deviation. It's called the standard error. That's interpreted in terms of the dependent variable. So what is the scale of the dependent variable in this case? Okay, which one is a dependent variable? Okay, and the y, what is the y? Real world grade, it's the grades, right?
Yeah.
Okay, what's the scale of our grades? 1 to 100, or 0 to 1, Okay, that's the scale. So what I'm saying is that the standard error, that number, is expressed in terms of that scale, 0 to 1. You can convert that to grade points if you want, but what is the output there? It's going to tell you that there's actually, I think this might be, let's see, 0.9. I think that's wrong. It's 0.09. The standard error is going to read 0.09, and that's reported on a scale from 0 to 1. You can convert that to points and say, okay, it's 9 points. Well, what that means is that you have an estimate here of a 73, let's say, or in this case, I changed it up, I guess. You're estimating 63, and what you're doing is, after that, you have to look at standard error to figure out, I may easily get 9 points above or below that. Is that acceptable in this case? Do you like that? Is that an acceptable risk, right? So what would you do in practical terms? We've decided we don't like that risk, the standard error above and below that line, above the grade. What do we want to do?
You study more.
Study more until you get to a point where it's estimating a grade that you like, but it's also the variance begins with the grade that's acceptable and then works itself up. Okay, so that's how you could use regression in practical terms. Here you can gather data and look at, you get an estimate, and then also figure out what's the risk. Finally, you have to check. There is a number of checks. You've gone over this in stats class. You may remember something called a p-value and a significance test. And what that does is it looks at the data and it estimates whether all this might be a mistake, whether all this, if there could be patterns in the data that show that the results are pretty likely to occur by chance. And if that's the case, then these numbers could be arbitrary, they could be bad. You could be looking at results and acting on them, and they could be wildly off. Like we said before, if you tried to use the mean, you were making a decision on the mean and you had an outlier, that would be a problem. You'd be making a bad decision because the figure is bad. Okay, so in this case, the rule of thumb is a 1 in 20 chance is acceptable. You always have the chance that the data could be garbage, that there could be a problem, who knows. But you have to move on and make a decision in the real world, right? So the rule of thumb is, well, 1 in 20 chance is acceptable. I'm willing to act on this data even though there's still a chance that it's garbage, but if there's such a remote chance, I don't care. I'm just going to keep going. And if you look over here, that's where you're finding that chance there. The chance here of this being data, where there's something wrong with this data, the data is that you're reporting merely represents some random chance event rather than representing something that's reliable. In other words, if I did the same study again, if I gathered the data again, what's the chance I would see the same stats? And the chance is pretty good. The chance is, in this case, there's only a less than 1% chance that I would see different stats if I ran this whole study again. That's acceptable. All right, so those are the 4 numbers you need to pay attention to, and that's kind of what they mean. All the stuff that I just talked about is all here, and so you could refer to that and as your notes, etc. And here's the Excel output, so that helps you to, when you do the Excel output, that helps you to interpret that. Now, PHStat will also call this p-value, so just be aware of that. Okay, so you have all those. There's a ton of extra stuff in there, and I also have some information about how to, communicate about this, how to think about it. And again, I would recommend using the thesaurus at all times. Just, whenever you're trying to describe something, it helps enormously to have additional terms to help you understand it. Here's the rule of thumb I was talking about. Typically, variance explained. I've seen this several times where they'll say, well, if it's less than 30, then it's weak. If it's between 30 and 60, it's a moderate, and more than 60 is strong. I mean, I've seen many, many studies in which it's been near 20 or less than 20, and they were still very happy. It still depends on the situation. But if you want a rule of thumb, the rule of thumb is there too.